Okay, so now we're back to talking about special types of the randomized comparative design. So our first one is called block design, and this is the experimental version of our stratified random sample. We break our subjects into two or more groups with these similar characteristics. Like we may break up into groups like male and female, so among gender. We may do age groups like 20s, 30s, and 40s. And we break them up along with similar age groups. So then from there, we apply control and treatment. So block design, these blocks are controlling for the effects of these lurking variables like age or gender. So if we think that age may also play a role, or gender may also play a role, we can block for those to make sure that that isn't affecting our results. And so here's a sample block design right here. Anne is an avid baker who would like to compare two different chocolate chip cookie recipes, recipe A and recipe B. So she recruits 10 volunteer taste testers. Woohoo! I like cookies too. To rate each type of cookie on a scale from 1, which would be very bad, to 5, which is very good. She will make 10 of each type of cookie. So 10 of type A, 10 of type B, for a total of 20 cookies. Each cookie tray, though, can only hold 10 cookies. So she's going to use 2 trays, and she's going to bake them at the same time in the same oven. So I don't have to worry about, well, the oven's been on longer, and so it'll affect the difference. The oven's been on the same amount of time, all that sort of stuff. But one will go in the lower rack, and one will go in the upper rack. So she's trying to deal with the whole making sure it's the exact same amount of time, making sure it's the exact same temperature, making sure all that sort of stuff by cooking them at the same time. But because the racks, now she's got to break it up. So here we have our blocks. We've got the top rack and we have the bottom rack. And each tray has the 10 spots. So we randomly assign our cookies to top rack and bottom rack. No. We randomly assign our trays to top rack and bottom rack. Hoping that the trays were same to begin with. Then I'm randomly assigning 5 of the type A and 5 of the type B because I want it to be even on the top rack and even on the bottom rack. So I randomly just do 5 type A's, 5 type B's on there, and I'll probably even randomly assign the position. On the tray. Because if you've ever baked cookies, the ones near the edge of the tray cook faster than the ones in the middle. The ones in the middle tend to be more doughy. So we're randomly assigning the cookies in a spot. We have 5 type A, 5 type B. We're randomly assigning cookies on the bottom, 5 type A, type B. And this is where we're dividing up based on that treatment. And then we're comparing our results. We're going to compare results up here. We're going to compare results here. And then we compare one more time all together, looking at all those differences. So it's almost like we've got 2 different experiments going on at the same time. We've got our top rack experiment and our bottom rack experiment. Okay, and that's our block design. Now our next one is a matched pairs design. I highly recommend you take a minute and you pause the video so you can fill in your blanks, because your whole chart here is blank right now. For some reason, I forgot to type this up when I typed up your notes. So I have all of this in here, and I'd like you to just pause your video and go ahead and fill in your blanks. Okay, so our next one is the matched pairs, and the name is very creative. Okay, no, it's not. I'm just being sarcastic. Matched pairs is really how it sounds. I try to match similar things up together, paired up, So that way I have people that are the same age, same body type, same maybe family medical history. And so I'm using all of this to help control for all of these lurking variables so I could truly measure the differences. And if I can't find people who are really similar, what I could do is I could use the same person and experiment on them twice. And so you've got those two options, so either similar people or I experiment on the same people twice. And what you do for your experiment has to be the same. So if I've got 10 people, I'd experiment on the same 10 people twice. Or if I have 10 people, I'm going to pair them up into pairs of five pairs that are very similar in nature. So that way I'm controlling for all of those lurking variables. So matched pairs is still a randomized comparative experiment, but it's also special block. I'm blocking for tons of different things when I'm pairing these people up. And then what we do is once we have people paired up, I randomly, when they're paired, I randomly assign one person to one treatment, one person to the other treatment. If I'm dealing with one person, then I randomly assign them to one treatment first, and then they have the second treatment second. And so some people may have the inactive treatment first and the real treatment second, and some people may have the real treatment first and the inactive treatment second, to go ahead and control for the possibilities of, well, if everyone has one first and everyone has one second, are we really measuring the differences there? So by randomly assigning which one, you get that you're controlling for those chances. You use that chance variables. So, sample matched pairs design. Is standing pulse rate different from sitting pulse rates? A class of 32 students is going to test the theory. I actually only have data points for 16. So go ahead and cross that off and write 16. And preferably not in yellow so you can read it. So we actually have data points for 16 students and they're tested in theory. They arrange the classroom alphabetical order, and they assign a person a single digit number from a random table of random digits. All subjects assigned an even number would stand first. All subjects assigned an odd number would sit first. They will be in their assigned position for several minutes, letting their body get used to the position. They will count their pulse rate for 1 minute, record the value, and then switch. Again, waiting for their body to get used to the position before taking their pulse. And then we compare the difference between the positions. And we're comparing standing minus sitting. And so over here we have our standing pulse rates. Over here we have our sitting pulse rates. And then we subtracted them. We have a dot plot that shows those differences. And I even went ahead and wrote out the statistical summary. So here's our mean. Here's our standard deviation. So the average difference is -0.8. The average distance from that is 6.4. So it looks like here's my mean. The average distance would be about here. And then we're not going to talk about standard error yet. That's more of a second semester thing. And then we have a minimum, we have a first quartile, we have a median of -2.5. We have a third quartile, 5.5, and a max of 10. So it looks like there's our median. Our interquartile range goes like this. Really close to our standard deviation. Showing that there is some skewness, but not a lot. It looks pretty balanced on both sides. So what would we think? By looking at this, do you think that there is really a difference between standing pulse rate and sitting pulse rate? And I would say that there's probably not enough of a difference. We don't see a huge amount on one side of the zero or the other. It seems pretty balanced. Our measures of center are really close to zero. And I would say there's not enough evidence. And then you'd want to explain why you think there's not enough evidence. If you look at our measures of center, they're both really close to 0. If you look at the balance between both sides, it almost looks uniform. There's only a couple spots where we really have peaks. So there's really not enough evidence to say that there's a difference between them. Some people did, some people didn't. And again, it could be the excitement or the boredom, or someone farted while they're in the middle of it. I mean, there could be all sorts of reasons for that. And I wouldn't say there's enough of a difference. Now, second semester, we're actually going to do the statistical tests that'll tell us, is there a difference or not? Is there really something going on here? And so that's our second semester, really delving deep into how can we tell this. Everything first semester is laying that foundation. Okay, and the last thing I want to talk about is statistically significant. And this is a really, really important thing, because this is our basis for all of our stuff. And so this is when an observed effect is so large that it could rarely occur by chance. For example, on our dot plot, if this was our 0 line and all of our dots were over here, that looks like big enough of a difference from 0. Everything's over here. That I would say that there's probably a big enough difference, it's statistically significant. There's probably a 0% chance that that would just happen by chance. By chance, the people we picked, and that day we got all those values to be right there, all huddled together and all that sort of stuff. What we had was a very by chance, you can kind of tell there's no pattern to it, there's nothing there. It's not statistically significant that there's a difference. So there's probably a 1% chance that this would happen just by chance. And we're actually going to do an activity talking about how can we tell if it's statistically significant? How do we determine that that's just by chance, or if that truly happened and that's a true result? And we'll do an activity in class on that and talk about that. And hopefully that'll give you a better idea of this.